Hi guys, my name is Mark. I'm studying engineering at Trinity College Dublin, and today we're going to be tackling question 12 of the Higher Level Physics 2020 paper. Specifically, we're going to be looking at a question that has multiple parts. It's 4 parts and you have to do any 2. And kind of the way that these parts come up is they normally pick like a part from different chapters. So you might have a question on mechanics, one on waves, something on electricity perhaps, and this question is worth a total of 56 marks, 28 marks for 2 different parts. Yet again, you can pick whichever one you want to do. And yeah, let's get straight into the question. In question 12, we're going to start with part A, and part A tends to be a question on centered around mechanics. The main 2 topics that normally come up are maybe a question on something like gravity, which is the case here, or another topic that comes up all the time in this part of the question is simple harmonic motion. So because this question is kind of dealing with space and planetary bodies, we're going to be working with Newton's law of gravitation, maybe even Kepler's law, and a few other important formulas. So yeah, let's get straight into part A. In part I, we are asked to derive an expression for the period of orbit t of the moon when it has a radius of orbit r around the Earth. We're also told here that the mass of the Earth in this case is given by m. Whenever you see a question like this and it kind of asks you to derive an expression, it basically is looking for a final answer that looks like a formula. And it tends to be kind of a formula that you know very well. So in this case, the formula that you're looking for is Kepler's formula, and you might have used it before to calculate different things like the orbit of a planet around the sun. But in this case, we're actually asked kind of where that formula comes from and how we can actually create that formula. The unfortunate thing about these types of questions is that there is a key observation that you kind of have to make, and it can be a little tricky to spot at first. You know, you might be able to see it from practice, but after a while of doing these types of questions, you begin to pick them up more and more, and you kind of get those connections a little bit easier. In the case of this question, it's kind of relating to the 2 forces, or I should say the forces acting on the moon and the Earth. Here below I have a rather poorly drawn diagram of the Earth and the moon orbiting around it. So here in the center of orbit we're going to have the Earth, and then also up top here we're going to have our moon. Now the important thing to note here is that the Earth and the moon are kind of related in some way, and that is by the force of gravity. So I'm going to just represent that by this little purple arrow here between them. And as we all know, the moon orbits around the Earth and it doesn't fly off into space. That's because the gravitational force exerted by the Earth is keeping the moon in place. Another way you can look at this is you can see that the moon is actually moving in a circular path around the Earth. It's actually being kind of kept pivoting around this central point that the Earth is on. And the way we can represent that also is by using another force, the centripetal force. In this case, the gravitational force and the centripetal force are exactly the same. They are actually just 2 different ways of saying the same thing that is keeping the moon orbiting around the Earth. Now that we've made this observation, it means that we can actually use the formulas that we know for representing the centripetal force of a body going around another one, and also the formula for gravitation, so Newton's gravitational formula, and we can actually allow them to equal to each other because we now know that they're the exact same force in this instance. Writing that down, what we can say is that the force of gravity, so gravity here being in my subscript, is going to equal to the centripetal force present in the interaction between the Earth and the moon. So it's going to be equal to the F, which is our force, and then it's going to be centripetal. So sometimes I make that misspelling mistake. It doesn't really matter. But in this case, it's just kind of trying to illustrate a little bit better. Because this force is kind of being, you can look at it in 2 different ways, but it's exactly the same force. It means that we can now find the formulas for these 2 forces and actually allow them to equal and rearrange to find what we're looking for, or hopefully at least get a little closer to our final answer. As always, if you need to find a formula, it goes straight to the log tables every time. You don't want to make a silly mistake kind of copying a formula down wrong or trying to, you know, save a minute on time. That minute is wasted if you don't get the marks for it. So in this instance, just go straight to your log tables to find our formula for gravity between 2 bodies and our formula for the centripetal force acting on the moon in this case. Here on the gravitation section of our log tables, we have Newton's law of gravitation, and the force of gravity in this instance between the 2 bodies is represented by this formula here. F is equal to G, which is Newton's constant, times the mass of the first body times the mass of the second body, all divided by the distance between them squared. Another formula that was key in this was the centripetal force acting on the moon, and it's represented here by, in the motion in a circle section, the centripetal force is equal to, we have two different formulas that we can use to represent it, and it doesn't really matter which one you use. You might need to do another step somewhere along the way in terms of manipulation, but in the end you should reach the same answer. Now, going back to our question, I'm going to write down our two formulas. So we're going to say that the F for gravity is represented by G times M1 times M2 all over D squared, and we're going to let this equal to our force, our centripetal force on the moon, which is represented by the formula mv squared all over r. Now, you might notice we have a lot of kind of different things going on here, and it's important to make sure you label things correctly. So in the case of the formula for the centripetal force acting on the moon, the mass here is going to be the mass of the moon that is, important here. So we can label that as saying M2 being the mass of the moon. Another thing to note here is that the or in this instance is the radius of the radius of orbit of the moon, and that is common. It's the same as the distance between the two bodies, so we can actually change that. If you wanted to rewrite this, you could say that they were both d in this instance, but because in the question we are actually told that the radius of orbit is given by this letter, the capital or, we can change both of those as well. Writing those in now, we're going to have capital or on both sides. The final change we can make to our two formulas here is that in the formula for gravitation, we have the we have m1, which is the mass of the Earth in this instance, and in our question we're actually told that the mass of the Earth is given by this letter capital M, so we can actually change that out now to kind of complete all of the necessary changes we need to make to the formulas. Changing that now to our capital M, we're ready to go in terms of manipulating these two formulas. Noticing on both sides we have M2 common to both sides, so we can cancel those straight away. And as well as this, we have OR common to both sides on the bottom, so we can actually cancel the square here with the other one over here. And what we get left with is V squared is going to equal to G M all over R. Finally, we can actually take the square root of this to get V squared on its own. So therefore, we can say V is going to equal to the square root of G M all divided by R. Now you might be asking kind of, well, what use is this? We now have an expression for the velocity of the moon, and we don't really care about that. We were actually asked about the orbit t, and that's the important thing to know here. We were asked about the orbit t, which is the amount of time it took to go around the moon. And this kind of key piece of information is found in the log tables as well, in the section on circular motion, but also waves, as in the wave section we have different formulas relating to the frequency and, more importantly, the period, or the amount of time it takes to complete one full revolution. Going to our log tables in the simple harmonic motion section, and we have different formulas here representing or actually telling us about the period. So in this case, the period is capital T, and it's equal to 1 over F or 2 pi over omega. Now you might be kind of stuck in this instance because in the previous question we found velocity and we didn't find F, or we didn't find omega. So you might be asking, how do we relate them together? And this is where we need another formula coming from the circular motion section. Going back to the circular motion section, we can actually find a formula that allows us to relate the velocity to this letter omega, which is our angular frequency. So in this case, V equals RW is the key formula we need to convert this to get our final periodic time. So if you wanted to actually break this down, what we want to do is we want to find omega on its own, so we can divide both sides by or, and we get V over or. Taking both these formulas back up to the top, we can say that omega is equal to V over or, and we can also say that our periodic time is given by T is equal to 2 pi all over omega. If we wanted now to sub in our expression for omega, this means that we can say that T is equal to 2 pi all divided by V over or another way of writing this is 2 pi or all divided by V. This is now where our previous thing, or finding the velocity, comes into kind of its own, because we have now found an expression for our periodic time using the letter V. So in this case, we can actually plug in what we found earlier and begin to solve for T on its own. So what we know here is that T is going to equal to 2 pi, and previously we had written it as little or being the radius of the circle, in this case the radius of the orbit of the moon, but because in the question we were told that this is represented by the letter capital or, we're just going to sub that in now, and then we're going to have V here on the bottom. So V, we said, was root G M all over or. Now technically this formula is correct, and You can use this in this current form. However, if you were trying to be perfect on this and you kind of noticed that in your log tables you had a different formula, the way you can find this is by squaring both sides and rearranging. If we square both sides, you have to square the left-hand side, so this is going to give us t squared, and then squaring the right-hand side, we have to square the top and then square the bottom. Squaring the top, we're going to get 4 pi squared or squared, and then on the bottom, we're going to get the square here, cancelling with our square roots, we're going to get gm all over capital R, and then rearranging this, finally, we're going to get t squared is going to equal to 4 pi squared, and then R cubed, all divided by gm. If you want to double check this, you can actually verify this formula by looking in your log tables in the section on gravitation. I think it's going to have Kepler's formula, and this is the exact same as Kepler's formula, and this is the derivation for it, and it really all kind of just depends on that observation that the gravitational force, which is keeping the moon orbiting the Earth, is exactly the same as the centripetal force acting on the moon. And once we have those two formulas, we can equate them and begin to solve for our final formula, which here is t squared is equal to 4 pi squared or cubed, all divided by gm. The mark breakdown for this question goes as follows. There was 12 marks going in total. There was 3 marks for making the observation that the gravitational force and the centripetal force were the same, and getting this section of the answer saying that the two forces, or should I say the two formulas, are equal to each other. 3 more marks were going for finding this expression for velocity on its own. In this case, you could have had just velocity on its own, or v squared also would have worked perfectly. And another 3 marks were going for this expression over here for the periodic time in terms of your radius and your velocity. You got your final 3 marks for correctly getting to the formula here that we got at the end. Just in this instance, because in the question, or should I say in your log tables, you see t squared is equal to, and then the rest of your formula. If you were to leave it like this, it's probably not best, and then in this case, that's why I square it out, just because I wanted to make it match like the log table. And it gives you a bit of peace of mind, I guess, if you do square it out, because it means that if it works out and it looks like the one in the log tables, you know you're right for certain. In part 2, we were asked to calculate the period of the moon as it orbits the Earth. Keyword here being the period, and as well as this, we're told that the moon is orbiting the Earth. Now, yet again, there is a formula that you want to use for this. It is Kepler's formula. It is given in the log tables, but because we actually just derived the formula in the previous question, I'm just going to take it straight from there. If you recall, the formula that we derived was that t squared is going to equal to 4 pi squared or cubed, all divided by gm. Now, just to be 100% clear here, m here is being like the mass of the body that is at the center of this like rotation. So, for example, since we're asked to find the period of the moon as it orbits the Earth, m here is actually the mass of the Earth. Now, this formula, yet again, as I was saying, given in your log tables in the gravitation section, I'm pretty sure. If you didn't derive it correctly, I want to be 100% certain, I would say you rip it straight from there. There's no point in making a silly mistake here, accidentally even. And you might notice here in this case that we have a load of letters that we have to kind of fill in. 4 pi squared and g are just constants that we already know. G is also found in your log tables under the constant section, but we actually have R cubed and we have M here being, so this here being R cubed and M being the two things that we have to fill in ourselves. Going back to the question given to us, you might notice at the bottom of it we were given this kind of block of text, and what we're told here is various figures for the mass of the Earth, the mass of the moon, the radius of the moon, and the radius of the moon's orbit around Earth. And the reason that they're given to us is because sometimes, obviously they're, sometimes they're not given to you, but they're not in your log table as well. So these are the figures that they want you to use. Because in our question we are asked about the moon orbiting the Earth, should I say, we need to know the mass of the Earth, and we also need to know the radius. So in this case, we're going to be using this top piece of information here, the mass of the Earth, and we're also going to be using this bottom piece, the radius of the moon's orbit around Earth, being given to us in meters. As always, everything has to be given to you in SI units. So in this case, if you had to work with the radius of the moon, you'd want to be converting this kilometers into meters. But as it stands, the two highlighted sections are given to us in SI units, so we should be fine on that. Now all we have to do is substitute in what we know. So we're going to say we're going to have 4 pi squared and then r cubed. So we said that r is going to be 3.85 by 10 to the 8. And that all has to be cubed, all divided by G times M. G here is Newton's gravitational constant given to us in the constant section of your log tables, and it is 6.7 by 10 to the minus 11. And finally, we're going to have M here being the mass of the Earth, which is given to us as 6.0, or just 6, times 10 to the power of 24. Important thing just here, like a little side note, is that sometimes, I remember especially when I was doing the Leaving Cert, I would always forget to kind of cube the radius here, because the radius is so massive. You know, you have by 10 to the 8 already there. Sometimes I'd forget that you have to cube all that, because you already have like that to the power of 8. So just kind of important thing to watch out. Pulling up my calculator here, I'm going to feed in all of the information. So we're going to have 4 pi squared, so pi yet again, shift, and then you have to do that, and then you're going to have this times the square, and then parentheses here because, or should I say brackets, because we're going to be filling in our radius, and we're raising that to a power, so it's 3.85 by 10 to the 8, and then closing brackets, and to the power of 3, and then on the bottom side of things, we're going to have Newton's gravitational constant, which was 6.7 by 10 to the minus 11, all multiplied by this mass of the Earth, which is 6 by 10 to the 24. And once you write down this formula, you know, even if you accidentally put in something wrong, you're going to be getting marks straight away. So this means that we're going to be given this value here, which is 5.6 by 10 to the 12 or so, and that's going to be our calculated value. So coming back to the question here, we're going to have t squared is equal to 5.6 by 10 to the 12. An important thing to note here, and something that people forget all the time, is that this value here is actually t squared. And what we need to do is we were asked for the period, so not t squared. So that means that t is going to be the square root of 5.6 by 10 to the 12. And I'm going to pull up the calculator and do that as well. Pulling up your calculator here. So pulling up your calculator, we're going to have the square root of 5.6 by 10 to the 12. Just to kind of tip here, if you want to be extremely accurate, you can use answer. In this case, it's just the answer that we got from the last sum, which was 5.604, something like that, and loads of decimal places. Either one is acceptable. You're not going to lose marks for a massive rounding error here, because they're really just looking for you to understand how to use the formula. So we're going to take the square root of our previous answer, which is going to give us this value here, and this is the answer that we were looking for at the end. I'm now going to summarize it in scientific notation, but they will also accept it in that form as well. So writing this down in our scientific notation, it's going to be 2.37, we're just going to round that up, by 10 to the 6, and this is going to be using the SI unit of seconds, because this is looking for a time, so time in this case is measured in seconds. The breakdown for this part of the question was there was 6 marks going in total, and you got 3 marks for correctly filling in the formula that we derived before, or if you just took it straight from the log tables, that's also fine. And then you got 3 more marks for your answer here at the end. And just a quick tip yet again, coming back to this, always remember here that this is t squared and it's not t, so make sure you have to take the square root to get your final answer. In part 3, we were asked to calculate the gravitational force exerted by the moon on an astronaut of mass 80 kilograms when he is 250 kilometers above the surface of the moon. So this is a very straightforward question, using kind of information that I was just saying earlier was given to us at the start of the question. And yeah, we're going to be using the gravitational force formula, which we talked about in part 1. But if you can't remember it, we'll review it again from the log tables. So coming back to our log tables again, just to double check here, we have Newton's law of gravitation, and it's going to be given by F is equal to G times M1 times M2 all over D squared here being the distance between the two bodies. So writing down that formula, F is going to equal to G times M1 times M2 all over D squared. And now all we're going to do is begin to fill in the information. As always, G here is just going to be, G here is just gravitational constant. It's 6.7 by 10 to the minus 11, and as always is given on the constants page of your log tables. As well as this here, we're looking for the mass of the moon. The mass of the moon is given to us at the start of the question, and we'll just go back up there to review it, because there's actually another piece of information given to us up there relating to the radius. Going back here to our kind of constants that we were given, we're looking for the mass of the moon, which is this underlined number here, 7.3 by 10 to the 12, or 22, should I say, kilograms. And another piece of information that we're going to be using here is this value for the radius of the moon. Now, as I was saying here, we need to make sure that we convert that from kilometers to meters. The reason is, as always, anytime you're using a formula, you need to use SI units. So to convert that, we're going to have 1,700, or should I say 1,740 kilometers, and then to convert that to meters we divide by 1,000 because there's 1,000 meters in a kilometer, and that's going to give us 1.7. Oops, sorry, classic mistake here. We're going to be actually multiplying, because if you were dividing by 1,000, you'd be changing the units in the wrong way. So we're going to be doing 1,740 kilometers times 1,000 meters to give us our final answer for the radius of the moon. Coming back here, we're going to be inputting the mass here of the moon to be the mass of one of the bodies. So the mass of one of the bodies, as we said, or as we saw at the start of the question, was 7.3 by 10 to the 22 kilograms. And then we have our other mass, which is the mass of the astronaut, which is given in the question here, 80 kilograms. And then you divide all of this here by d squared being the kind of radius between the two of them. This is kind of the place I would say that most people would lose marks, because they would see 250 kilometers here given in the question and go, all right, so 250 kilometers, convert that to meters, maybe that would be our radius. But in actuality, it's going to be a little bit more complicated than that. Because the person is, or should I say the astronaut is orbiting at 250 kilometers above the surface of the moon, it means that we have to add on the radius of the moon as well. The reason of this is because the formula given here, Newton's gravitational formula, this d squared on the bottom is the radius of the orbiting body from the center of gravity. And the center of gravity here of the moon is going to be at its very core. So what we have to do is we have to add on a little bit more. We're going to have 1,740 kilometers, which is the radius of the moon. We're going to have to add on our 250, and then we want to multiply that by 1,000, because as always we have to convert that to meters, and then finally we have to square all that. So that's kind of how I would write it out, just generally, and then all we have to do is plug that into our calculator. So plugging that into our calculator, we're going to have our Newton's gravitational constant, so it's going to be 6.7 by 10 to the minus 11, and then we're going to be multiplying that by, here in our brackets, our mass of the moon, so it's going to be 7.3 by 10 to the 22, and then our mass of the other body, which is the astronaut, which is 80 kilograms, and then on the bottom half here we're going to have our d squared, so we're going to have, in here we're going to have 1740, which is our radius of the moon, plus 250, and then we're going to multiply that by all 1,000, and then closing our brackets, we want to square that because it's d squared, and then we press equals, and we're going to get our answer, which in this case is 98.8. So as always, you know, you can have slightly different answers here, and you might get something slightly different, but in this case 98.8 is correct. So we're going to write that down, and obviously don't forget to include your units. Our answer at the end here is going to be 98.8 newtons, and newtons here being our unit for force, and that's going to be our final answer. Yeah. The breakdown of marks for this question was a total of 6 were going, and you got 3 marks for correctly identifying this formula here for Newton's law of gravitation, and then getting another 3 marks for getting your correct answer. As always, depending on the value you use for Newton's law of gravitation, you might get a slightly different answer. For example, if you had a much longer, if you had a much more like accurate, use all the decimal places given in your log table, so that constant, you might get a slightly smaller number. But yeah, anything in and around here should be acceptable. In part 4, you're asked, astronauts appear to be weightless when they orbit the moon, and we're asked to explain why. So in this case, all we're doing here is just a simple theory question, and it might take a little bit of thinking to understand. But in this case, what is actually happening is both the astronaut and kind of like the spaceship that he's in, for example, they're both falling or free falling at the same rate. So you can think of them existing in the same plane, and both of them are falling at the same speed because there's no air resistance or anything that's acting on them. And because they both fall at the same speed, their relative velocities or motions, kind of to go in a little bit more depth, there is none. They're both falling at the exact same speed. So everything kind of appears stationary to them, and that's why they can actually feel weightless. The breakdown for marks of the section was there was a total of 4 going, and there was 4 marks for saying that they have either saying there was a common acceleration, or in this case, the word free fall also works. So you would get 4 marks for saying that being the buzzword. In part B, we were asked a question focusing more around heat and heat transfer, and these tend to have a little bit of an overlap sometimes with kind of just energy in general. So in this case, we're looking at a question about solar radiation falling on the surface of Antarctica, and we're asked a few bits of information, a few questions on kind of what radiation is, calculating energy relating to the radiation, and just a few other things like that. Similar to part 1, we're also given a little bit of information and a little bit of kind of constants at the bottom. So we're told here some information about the density of glacier ice, and there's a few others there as well, which we will probably use later on. If they give them to you, they tend to be used, so yeah, heads up for them later on. In part I, we were asked just a straightforward theory question. In this case, it is radiation is one of 3 methods of heat transfer. What are the other 2 methods? And this is just something kind of that you have to know. The answer is conduction, which is the passing of heat through solids, and convection, which is the transfer of heat by the circulation of kind of heated parts of a fluid or a gas. So in this case, these are your other 2 answers. There was a total of 6 marks going for this question, and the breakdown was fairly simple. 3 marks for getting each of these correct. In part 2, we were asked to calculate the infrared energy that falls on 0.25 meters of Antarctica in 3 minutes. So this question is centered around energy and calculating the energy falling on the surface of Antarctica. And there's also a time given to us, so that's going to come into it somehow. But the kind of best way to start with it is that in the start of the question and kind of in that introduction paragraph, we're given a little bit of information. In this introductory paragraph, we are told that the solar radiation that falls on the surface of Antarctica is 850 watts per meter squared. We're also told that 52% of the incoming radiation is infrared. Now, remembering back to the question we were asked in part 2, we were asked about calculating the infrared energy that falls on the surface. So this basically means that not all of the radiation on it is infrared, and we're told that 52% of it is. So that's also going to factor into our answer. Back to our question here, I'm going to write down what we know. We know that there are 850 watts per meter squared falling on surface of Antarctica. Another key piece of information we know is that only 52% of it is infrared. So basically that means that when we're asked to find the infrared falling on it, we're not looking for all the radiation, we're only looking for a portion of it. What you might notice here is that this is given to us in watts. Basically, that is a measure of power, and power has to take into consideration time. Watts in this case means that the amount of energy falling per second. So in this case, this is how we incorporate this 3 minutes to us given in the start of the question. So in order to solve this, what we're going to start by doing is multiplying this figure of 850 watts per meter squared, multiplying this by 0.25 meters squared, because what that basically means is if there's 850 watts per meter squared, then if there's only 0.25 meters squared, then there's going to be a little bit less. It's going to be a quarter. As well as this, we're going to also multiply by 52%. And the reason we're multiplying by that 52% is because we're asked about the amount of infrared that falls on the surface, not just kind of generally about all of the radiation. We're only asked about that infrared. Finally, we're going to multiply by 3 minutes. So if you want to be just write it out fully, we're going to have 3 times 60. Reason being for that is because we want to work with our SI units for time, and the SI unit for time is seconds, so we need to convert minutes to seconds. Once again, the reason that we are multiplying here by 3 times 60 is because at the start we said that 850 watts falls, and 850 watts is a measure of power, which means that 850 joules of energy fall on the surface per second. If we want to find the total energy, then if we have 850 joules times 3 minutes, that means the total amount of energy over the course of those 3 minutes falls on the surface. We need to find out what this is equal to, so all we're going to do is slap this into our calculator, and yeah, it's fairly simple from there. Bringing up my calculator here, we're going to multiply 850 times our 0.25 because there's only 0.25 meters squared available. We're also going to multiply by 52%, so 0.52, or you could just multiply by 52%. Oh, I have an extra multiplication sign in there. And finally, we're going to multiply by 3 times 60, and we're going to use those brackets there just to make sure that it does it all kind of together. And you could also multiply this by 180 if you knew that off the top of your head, and we're going to just get that to equal, and the answer we get is 19,890 joules. So writing that down here, we're going to have 19,890 joules, and joules here being our SI unit for energy. The question is calculate the amount of energy, so we're going to be using that SI unit. Alternatively, you could write this as 19, 0.89 kilojoules if you wanted to do it that way, but it doesn't really matter. They're just kind of different ways of writing it. The breakdown for marks for this question was also fairly simple. There was 6 marks going in total. You got 3 marks for correctly identifying the 850 joules and the 52%. You also got another 3 marks for including your 0.25, your 3 minutes, and also getting your answer at the end. In part 3 of this question, we were asked to calculate the number of infrared photons that fall on this area in this given time. So this is kind of based off what we found before. And because it's asking a question related to the one before, your answer that you're going to be using, you got from before, we're also going to use here. So if you got a slightly different answer before, maybe you made a mistake along the way, you'll lose marks probably here for having that wrong answer, but at the end of the day, you'll get marks for the procedure or your method if you do it correctly, so it doesn't really matter. It's always important to kind of push on even if you get the last one wrong, because the examiner doesn't rob you of all your marks. They actually give you marks if you have kind of the idea and the method down. Coming back to this question, we were asked to calculate the number of infrared photons. So photons here being the kind of packets of energy that we find in this electromagnetic radiation, so in the infrared energy. We're going to be using a formula here to convert between energy and photons. The reason that we want to do that actually is because we need to be able to find the number of photons, which means that we need to break up that total amount of energy, that 19,890 joules, into how much energy each photon has, and then if we divide those, we should be able to find the number of photons required to make up that total amount of energy. The formula we're going to use is given in your log tables, and we're going to go straight to them in order to find it. As always, just kind of worth avoiding losing marks for getting, for making a silly mistake. So in this case, we're going to go straight to that. So here we are at the light and sound section of our log tables, and here we have our energy of a photon is given as E is equal to HF. In this case, if you don't know what H is Planck's constant, a constant given on the constant page of your log tables, and all you have to do is go straight to that and you'll find it as Planck's constant. So going back to our question, we're going to write down our formula. E is going to equal to HF, and this is the energy of a single photon. Now, you might be wondering how we're meant to solve this, and that's because we have this letter F here, which is the frequency of the photon, and we're not actually given a frequency in this kind of part of the question. But if you remember going back to our kind of like at the top of the question, there's like a little paragraph. It actually gives us a frequency in there, which is actually the average frequency of the infrared radiation. Going back to the top of the question here, as I was saying earlier, here we have a value for the average frequency of the infrared radiation being 15 terahertz, and 15 terahertz is like a really, really big number, so it needs to be changed to the SI unit for frequency, which is just the hertz. So to convert from 15 terahertz into just normal hertz, the prefix tera, also given to you in your log tables on the prefix page, is actually 15 times 10 to the 12 hertz. And that's basically how we convert, in this case, from terahertz into just regular hertz. Going back to our question at hand, what we're going to be able to do now is fill in the blanks. What we're going to say is the energy of a single photon is going to be equal to 6.6 by 10 to the minus 34, which is Planck's constant. And we're going to multiply that whole thing by the frequency, which we said was 15 by 10 to the 12 hertz. And plugging this into our calculator, we're going to get a value for the average energy of a single photon. So bringing up our calculator here, we're going to plug in what we know. We're going to have 6.6 by 10 to the minus 34, which is a really small number for Planck's constant, times our frequency, which is 15 by 10 to the 12. And that's going to give us a value of 9.9 by 10 to the minus 21. So this is going to give us our value of 9.9 by 10 to the minus 21. And because this is energy, we're going to be measuring this in joules. So what this basically means is we now know the average energy of a single infrared photon. And this is kind of important to us because we already know that the energy falling on this piece of Antarctica in this time frame, these 3 minutes, we already know that from our previous question. So if we know the amount of energy total and we know what one photon does, if we divide that total amount by what one is, we'll be able to find the number of photons required to make up that infrared energy that falls on it, which is kind of what the question here is asking for. Going back to the previous question, what we know is the answer we had was 19,890 joules. And what we're going to be doing here is if we divide that by the amount of energy of a single photon, or should I say the average, to be honest, we're going to have 9.9 by 10 to the minus 21 joules. And if we plug this into our calculator, we're going to be able to get a value for the we're going to get a value for the number of photons that it takes to the number of photons that hit the bit of Antarctica over these 3 minutes. So bring up my trusty calculator here. I'm going to fill in our fractions. So on the top, we're going to have 19,890 joules. And on the bottom, we're going to have our 9.9 by 10 to the minus 21, which is the average energy of one photon. Pressing equals here, we're going to get 2 and a low decimal places by 10 to the 24. And that's going to give us our number of photons that fall on this 0.25 meters or meters square of Antarctica over 3 minutes. So writing this down, we're going to have 2 by 10 to the 24, and that's just a number. Just if you wanted to double check that, what we're going to have here on our fraction is joules on the top and joules on the bottom. So those two units will cancel, and what we just get is a number. So it's just a number of infrared photons. So if you've kind of gotten this far, you're kind of right. The breakdown for marks goes as follows. There was also 6 marks going for this question. There was 3 marks going for correctly kind of identifying your formula and also finding this 9.9 by 10 to the minus 21 joules, the amount of energy that one photon has. And then you got 3 more marks for this line here, finding the the number of photons required to make that up. In part 4, we are asked to calculate the energy required to melt 0.5% of the Earth's glaciers if their average temperature is minus 6 degrees and the point of melting is minus 2 degrees. Now, this question follows like a little subparagraph in this question, which tells us a little bit of information about the Earth and kind of the effects of radiation and the heating of the Earth. And we are also told that the volume of all the ice glaciers on the Earth is 170,000 kilometers cubed. Looking back at our question, we asked to calculate the energy required to melt a portion of this ice. So whenever you think about kind of energy and melting and temperatures, you need to think about the temperature and that section of physics. And you're going to end up using formulas kind of relating to the specific heat capacity of metal, or in this case, it'll be probably ice or water, and also latent heat, which is another important thing as well, that formula as well. The question is kind of where do you start? So those formulas, if you recall just off the top of your head, you're going to need little, different pieces of information, but one of the important parts of it is mass. So what we were given here is the amount of, or should I say the volume of ice on the Earth. And what we need to do is find the mass of this ice. So we're given this 170,000 kilometers cubed, and we're given this 170,000 kilometers cubed. You might be asking, how do we convert this from a volume to a mass? And actually, the key to this is given in the question as well. Going back to the question kind of given to us in part 4, just underneath it, we are told this kind of little bit of information here. And one of the important pieces of information given to us is that the density of a glacier ice is 920 kilograms per meter cubed. So we can actually use this now as well as the density formula to find our mass of this 170,000 kilometers cubed. As always, whenever there is a formula that you need to use, in this case this density formula, the best place to go for it is your log table, so you don't make a mistake, because sometimes you can kind of misremember them in the exam. So we're going to go straight to our log tables to find this formula. Going to the forces and materials section of your log tables in the mechanics area, we're going to find this formula for density, which is rho is equal to m over v. In this case, rho is going to be our density, m is our mass, and v is our volume. Now we're going to write down our formula here. So we're going to say rho is going to equal to mass over volume. And now we're going to fill in kind of the information that we know. So we know that rho, our density, is given in the question, and it was 920 kilograms per meter cubed. We don't know what our mass is, so I'm just going to let that be m. And on the bottom, we're going to have our volume, which is 170,000 kilometers cubed. Now, first thing that should be kind of setting off alarm bells here is this kilometers cubed. This is not the SI unit for volume. What we need to do here is convert this to our SI units in order to correctly use this formula. Now, you might be wondering, how do I convert this 170,000 kilometers cubed into meters cubed? And, you might have various different approaches, but the following approach is kind of the way I always learned it and kind of the easiest way for me to understand it. What we have here is our 170,000 kilometers cubed, and what we're going to do is we're going to want to multiply this by this kind of scale factor. And in the bottom here, we're going to have our kilometers cubed, and the reason we want our kilometers cubed is because these two should cancel each other out, and on the top we'll have our meters cubed. And when these cancel out, it means that we're just going to have a number times some number of meters cubed, and that'll give us an answer in meters cubed, which is kind of what we're looking for. So now what we do is identify this kind of scale factor. On the bottom here, we're going to have 1 kilometer cubed, and basically it means that for every 1 kilometer cubed, how many meters cubed there are. Now, sometimes this can work the other way around, but you need to think about this kind of just rationally. If you have 1 kilometer cubed of volume, that's going to be a massive amount of smaller meter cubed. So it means that the number that you're going to be multiplying by is much bigger than 1. It's going to be massive. It's going to be a really, really big number. So it means that on the bottom we're going to have 1, and on the top we're going to have a really big number, which will give us yet again another really big number in terms of meters cubed. The question though is, what are we going to be multiplying by? And the simplest way to explain this yet again is just by using a little diagram. So on the right here, I'm just going to draw a small little cube. Now, apologies for the terrible drawing, but what we can do is think about this cube as having 1 kilometer sides. Another way of writing 1 kilometer is actually writing it as 1,000 meters. And if you extend this idea to the whole cube, what we're going to have is a three-sided cube, or not three-sided cube, but you're going to have a cube that's going to have sides of 1,000 by 1,000 by 1,000. And basically, if you convert that 1 kilometer cubed, it's going to be just 1 kilometer cubed is just 1. But if you wanted to represent that in meters, it's going to actually be 1,000 cubed meters cubed, because there's going to be 1,000 for the length times 1,000 for the width times 1,000 for the height. So that's the number we're going to multiply by. We're going to multiply by 1,000 cubed, and that's going to get us our meters cubed value. In order to find this, though, we need to plug this into our calculator, so that's what I'm going to do next. So now I'm just going to plug this into our calculator. So we're going to have 170,000, so 170 times 1, 2, 3 for 1,000s. We're going to multiply this by our scale factor, which we said was 1,000 cubed on the top. So raise this to the power of 3. And on the bottom, we're going to have 1 kilometer. So for every 1 kilometer, there is 1,000 cubed meter cubed. And then we're going to just multiply this out. We're going to get 1.7 by 10 to the 14. So this is converting the kilometers cubed into meters cubed. So let's write that down. We're going to have 1.7 by 10 to the 14, and that's going to be the numbers of meter cubed. So now what we need to do is just sub this into this formula to get our correct answer. Plugging this in, we're going to have m still on the top, but on the bottom now we're going to have this 1.7 by 10 to the 14. And now what we can do is rearrange to find mass on its own. In order to find mass on its own, what we're going to do is we're going to say m is going to equal to rho times v, which is just manipulating the formula that we had earlier. And that basically means that if we multiply 920, which is what we were given above, times 1.7 by 10 to the 14, we should be able to get our value. Another important thing to remember at this time is that we were asked about 0.5% of the Earth's glaciers. We're not asked about all of them. So at this stage, I'm going to multiply by 0.5% so that we can find the amount of mass that we're looking for. You can do this, you could multiply this out now and then multiply by 0.5 after, but in this case, that's just how I'm going to do it. So we're going to multiply by 0.5, so multiply by 0.5%. As always, here's my calculator, and we're going to do 920 times our 1.7 by 10 to the 14, and then we're going to multiply by our 0.52. 0.52, or sorry, when we get that 0.52, we're just going to multiply by 0.5%, which is what we were asked for in the question, so 0.5%. And that should give us an answer of 7.82 by 10 to the 14. That's the value that we get, and obviously you have to remember your SI units. So coming back to this question, what we're going to have is 7.82 by 10 to the 14. That was the value got on our calculator. And then this is obviously our SI unit for mass, which is going to be in kilograms. So this is kind of like the first step you want to do. You want to convert this volume of ice into a mass so we can then use that in our formulas for finding energy when it comes to heat transfer and stuff like that. As always, though, we need to ask ourselves a little bit more about what's going on with this ice. We're going to go back to the top of the question and kind of think about it and what's actually happening. So here we have the question at hand, and what's happening here is we're asked about the energy required to melt this ice. And what that means is that the temperature of the ice is -6 and the melting point of the ice is -2 degrees. So if you want to think about it, if we have ice at -6 degrees and we're applying energy to it, and we want it to melt, what's going to happen is some of that energy is going to go to increasing the temperature of the ice. The ice is going to slowly increase in temperature to -2 degrees. So that's like the first stage. The energy goes towards heating the ice. What's then going to happen is any energy that is supplied to the ice further than this is going to cause it to change state or go through kind of latent heat is kind of what the term is. So in this case, it would be the latent heat of fusion. So what's happening here is that the energy given to the ice is going to changing it from a solid into a liquid. So what's really being asked of us is how much energy is required to heat this ice from -6 to -2. And then as well as that, we're also being asked, as well as this energy to do that temperature change, how much energy is associated with changing all that ice from a solid to. All of these changes are modeled by formulas which are given to us in our log tables in the physics section, specifically around temperature and heat and energy. So we're going to go straight to them to find the formulas that we require. In this instance, the formulas that we're going to need to use are going to be the energy needed to change temperature. So what we're going to be using here is delta E is going to equal to mc delta theta. And the reason that we're using this formula here on the left is because we have found a mass. And that mass is kind of important because here we have m in this formula. While in this formula over here on the right, there actually is no mass. So we're not going to use this formula here. We want to use the one on the left. As well as this, I said that we were changing state. So we're going from a solid to a liquid, which means we need to use this energy needed to change state. And yet again, for the exact same reasons, we're going to use the formula on the left, which uses this m symbol, this mass, and we're not going to use this formula on the right because this doesn't have mass included in it. Going back to our question at hand, I'm going to write down our formula. So we're going to have our energy required to change temperature is going to equal to mc delta theta, and the energy for latent heat is going to E equals ml, where L here is going to be our specific latent heat capacity of fusion because we are going from a solid to a liquid. Now, if we were asked to find the total energy associated here, what we need to do is actually write down kind of a formula for finding this. So what we're going to be doing is to find the energy and kind of say our subscript here, our total is going to be the amount of energy needed to heat the ice. So it's going to be mc delta theta. And then we need the amount of energy to change the state. So it's going to be ml. So we actually need to add these two formulas together. Now what I have to do is fill in what I know. Now, as I was saying earlier, we have found these values for m. As well as this, we also can find delta T very easily because we are told that the temperature of the ice started at is -6, and we said that it needs to reach -2, so you can just find the difference between the two of them. The only difficult thing here is going to be finding this value for C and this value for L. Now, you might be racking your brain going like, how do I find this? Is there another formula for it? But actually, very simply, it's also given to us in that little paragraph in the question. Alongside the density of glacier ice, we're also told the specific latent heat of fusion for the glacier ice, and also the specific heat capacity of the glacier ice, which means that we have our two values here for C and for L. That basically means that all we need to do now is start subbing in things. So what we're going to have is our energy is going to equal to M, which we said was 7.82 by 10 to the 14. And we're going to multiply now by C, which is our specific heat capacity of glacier ice, which is told to be in the question 2,900 joules per kilogram per Kelvin. And then we want to multiply here by our delta theta, which is our change in temperature. So here we're going to have a minus 6 minus, and then you're going to have your minus 2 in here. So make sure to include your brackets there because there's loads of minuses going on there. You can very easily mix it up. And we have to add on to this M times L. So M again is 7.82 by 10 to the 14. And we're going to multiply that by our L, which in this case is specific latent heat of fusion for the glacier ice, which is also given to us in the question, which is around 3.3 by 10 to the 5 joules per kilogram. Joules per kilogram. So that's the kind of the long expanded way out, and all we have to do is slap that into a calculator and we'll get an answer for it. So bringing up our calculator, we're going to fill in everything that we know. So we're going to have 7.82 by 10 to the 14. We're going to multiply that now by this 2,900, which is our specific heat capacity of glacier ice, and then we're going to multiply it by our change in temperature. So the change in temperature would be minus 6 and minus 2 if you just want to do it in your heads, or you can put it into your calculator, and that change in temperature is 4. And then we want to add on M times L, so we're going to have 7.82, which is our mass, 10 to the 14 should I say, and then we multiply by L. In this case, L is going to be our specific latent heat capacity, specific latent heat of fusion. So it's going to be 3.3 by 10 to the 5. And just putting that into our calculator, we should get an answer of 2.67 by 10 to the 20 joules. So now writing down our answer, we're going to have 2.67 by 10 to the 20. And this is going to be an energy, so this is going to be measured in joules. And that's our final answer. The total marks for this question were 10 marks were going, and the breakdown goes as follows. There was 2 marks going for correctly identifying the formula for density, and there was another 2 marks going for correctly finding the mass of the ice on Earth. There was another 4 marks going for correctly building kind of our formula for finding the energy required. In this case, it was broken down as having 2 marks for each term, so 2 marks for correctly finding the formula for the heat change, and 2 marks for finding the state change in this case. So we have our MC delta theta, that was worth 2 marks, and we have ML, which was also worth 2 marks. Finally, we get our final 2 marks for getting our answer, which is going to be 2.67 by 10 to the 20 joules, and this brings us to our total for this part of the question. In part C, we were asked a question centered around the kind of waves and kind of all the physics behind them. So in this case, we're asked a couple of questions about the Doppler effect and then the formula that you use in the Doppler effect as well. So let's get straight into part I. In part I, we were asked, what is the Doppler effect? And unfortunately, this is just kind of like a straightforward definition that you have to know. If you're really stuck, I suggest putting down the formula and maybe explaining the symbols in it. But in this case, you really just kind of have to know the theory behind it. The definition of the Doppler effect goes as follows. The Doppler effect is the change of observed frequency due to the relative motion between the source and the observer. It's important now that you include a few kind of like key terms when you're explaining this. In this case, one of the key terms is change of the observed frequency, and another key term is the second half of the question, due to the relative motion between the source and the observer. So for this kind of definition, you need to know it in its entirety in order to get all the marks. There were 6 marks going for this definition, and the breakdown was fairly simple. There was 3 marks going for getting the first half of the definition right, so saying that there was a change of observed frequency, and there was another 3 marks going for saying that this was, what causes this, the relative motion between the source and the... In part 2, we were asked to explain with the aid of a labeled diagram how the Doppler effect occurs. Now, in this case, it's also a definition, but you need to have that labeled diagram, and always, as always, make sure you don't forget the labels, because sometimes, I know I did, So here is my rather crudely drawn diagram. It doesn't have to be a work of art, and I'm going to fill in the labels as we go through it. So what we have here on the right is our observer. And what we can say, or what we know, is that this guy is stationary. What we have on the left here is a series of rings with a kind of a source that they are emanating out of. So what we have in the center of these rings is a little source. And this source in this instance is moving. My other little arrow down here at the bottom is kind of pointing to how close the rings are on this side. And it kind of basically just shows that the wavelength in this area is shorter, and we can see that because the crests are closer together. As always, your diagram doesn't have to be perfect, and I kind of really encourage you to know your diagrams well, because if you get into the exam and you can remember the diagram but can't really remember the definition, you can actually use the diagram to kind of build the definition and scrape together some points, or should I say marks. So now that we've had a look at the diagram, we're now going to go through the kind of how the Doppler effect actually occurs, and we need to, have a little block of text explaining it. As always with these types of questions, there's keywords you need to include, and in this case, we're going to have a look at those. The definition for how the Doppler effect actually occurs is as follows. The source of sound moves towards the chosen observer. As the source moves, the sound waves move out in a non-concentric circle fashion. This results in the incident wavelengths on the observer being shorter and thus a higher frequency. Now let's break that down by the key points. One of the key points here is labeling and including these non-concentric circles. Basically, as we saw in the below diagram, we saw that those circles were kind of pushed off to the right-hand side, and they were getting kind of pushed off more and more. And that's basically what these non-concentric circles are. As well as this, another important thing to include here is that the sound, or should I say the source of the sound, moves towards the actual observer. The other two important points to include here is that the wavelengths to the observer got shorter, and that the final frequency was also higher as a result of these shorter wavelengths. There was a breakdown of 8 total marks going for this question, and they kind of were separated as follows. You got 2 marks for including each important kind of like key point, and there were 4 key points to include. One of them was that the source of the sound moves towards the observer. Another one was that there was a non-concentric circle. That's how the waves were spreading out. As well as this, we need to include that the wavelengths in fact got shorter, and ultimately that resulted in a higher frequency. In part 3, we were asked a question on waves that is less about the theory and more about the maths. What we're told is that there is a source of sound that is approaching a stationary observer. We were also told that that source appears to have a frequency that is 20% greater than the frequency it has at rest. We were finally asked then to calculate the speed of the source. Now this is a little bit, it might come across as a little bit challenging at first, because what we know is, well, we know very little. What we know is there is a frequency that appears to be 20% louder than it is when moving than it is when it is stationary, and that's about it. We need to be able to calculate the speed of the source from this kind of very little information. One thing to note here is that in the question body at the start, we were actually told the speed of sound. It's very usual for these types of questions to give you a definitive number, because sometimes it can change, and they don't expect you to know it off yourself. So in this case, we are told that the speed of sound is actually 340 meters per second. So that's kind of another piece of information that we now know. So how are we meant to kind of work with this? This question asks us about a stationary observer and a moving source. So what we're being asked about is the Doppler effect here, which kind of goes along with the theme of the whole question. Because we're being asked about the Doppler effect, it means that we're probably going to end up using the formula for the Doppler effect, which can be found in our log tables. So in this case, I would just go straight to my log tables and write down that formula and see if there's anything that I can kind of use that to figure out. If we go to the light and sound section of our log tables, the second formula down, we're going to find our formula for the Doppler effect. And here we see this formula over here. Now, what it says is f prime, which is the perceived or apparent frequency, is equal to the frequency at rest times the speed of the wave in whatever medium you're kind of interested in. So in this case, we're interested about the speed of sound, and u here is also the speed of the observer. If we go back to our question, I'm going to write down that formula. We have f prime is going to equal to f c times c, and then we have plus or minus u. Now, the important thing here is determining actually which symbol it is, and that's dependent on which direction the source of the sound is moving relative to the observer. So in this case, because the source of the sound is approaching the observer, what we can tell is that the formula takes on the form f prime is equal to fc all over c minus u. So basically means it's coming towards the observer. So now that we have our formula worked out, we now need to kind of work with what we're given in the question. What we're told is that the apparent frequency is 20% greater than what it is at rest. Basically, if we were to write that out mathematically, the way we would describe that is we would say that the apparent frequency f prime is equal to 1.2 times the frequency at rest. And you can kind of think of this as, you know, the apparent frequency is going to be the normal frequency and 20% extra. So that's where that 1.2 is coming from. It's 120% of what it is normally, so 20% extra. And that's kind of the key insight, or the key observation you need to make, is because now that we have a formula relating f prime and f, and we have this other formula, we can now begin to sub stuff in. So what we're going to do now is plug in what we know. So now I'm going to plug in what we know. So what we're going to say here is f prime, now we're going to say that is 1.2. F is going to equal to f times c, which we said was 340 meters per second, all divided by 340 minus u. And now all we have to do is rearrange to find u. The thing we can do before we rearrange actually is that we'll notice that f is common to both sides. This frequency here is on both sides. We see it on the top as well, which means we can actually cancel them. So in this case, we can divide both sides by f, and that'll go away. So all we're left with is one unknown, which is u. Rearranging, what we're going to have is we're going to have 1.2 times 340 minus the letter u is going to equal to 340 itself. 1.2 times 340 is 408 minus 1.2 u is going to equal to 340. Rearranging this, we're going to get 1.2 u is going to equal to 68. Now, if we divide both sides by 1.2, we should be able to find what u is. And in this case, u is going to equal to 56.7 meters per second if we round up, making sure obviously to include your SI unit for velocity in this case, because we're asked about the speed of the source, so in this case it's a velocity, so meters per second. The breakdown of marks for this question goes as follows. There was 10 marks going for this question, and there was 4 marks for simply identifying the correct version of the Doppler effect formula, including this little minus down here, because you need to be able to tell which way which way the source is moving relative, and being able to reflect that in the formula. 3 more marks were going for this expression for the apparent frequency, using the information given to us in the start of the question, and another 3 marks were going for finally solving and getting an answer of 56.7 meters per second. In part IV, we were asked a very common question about the Doppler effect, which has got to do with red and blue shift of distant stars. In this case, we were asked about the redshift of the universe and what that kind of tells us. Now, I know the answer is right here, but I'm going to try and give a little bit more insight to what that means. The answer in this case is that the universe is expanding, and that's kind of reflected by the fact that there is a redshift in the light that we see from other stars. But we can represent this and actually show it in mathematical formula. The formula that we wrote down in the previous part of this question, the formula for the Doppler effect, was f prime is going to equal to fc times c plus or minus u. And basically, depending on whether the source is moving towards or away from the stationary observer, we get that plus or minus u on the bottom. So let's for a moment assume that the universe is expanding, which we already know it is, but let's just kind of assume it is. Basically, it means that we can rewrite this formula saying f prime is equal to f times c all over c plus u. Now, the reason that it is plus is because as we see this distant light from stars, and we can see these stars are moving away from us. If they're moving away from us, the version of the formula that says that the source is moving away from us involves this plus on the bottom. As a result of this, because we are adding things on the bottom, the denominator, which is this bottom half denominator, is actually getting bigger. This is what this little arrow over here means. It just basically means that the denominator is getting bigger because we are adding things on the bottom half of the fraction. As the denominator gets bigger, it means that the overall fraction will get smaller. And as the overall fraction, this is just kind of me symbolizing it, the overall fraction will get smaller. And as the overall fraction gets smaller, it means that this overall kind of the perceived light or frequency of this light will get smaller and smaller. Now, on the human spectrum, on the visible spectrum of light, electromagnetic radiation, as this frequency, as you get to the lower frequencies and drop it down, the lower frequencies of the electromagnetic spectrum that is visible is represented with the color red. This question asks us about the redshift of galaxies. So when we see galaxies turning, the light from them turning red, it means that these faraway stars are actually the apparent wavelength of this light is getting smaller, which is reflecting the fact that the universe is actually expanding outwards. The total marks for this section of the question was 4, and really there was only one key point here, which was that the universe is expanding. And that's where the 4 marks went. In part D of question 12, we are asked a question centered more around electricity. There tends to be one in these little 4-part questions, so we knew it was coming. And in this case, we are asked, we're told in the opening little paragraph, a little bit of information about the SI unit for current. And but the first part of this question is actually asking us about current. So let's get straight into that. In part I, we were asked a fairly simple question, which is, what is current? Now, in the exam, something so straightforward like this little definition can easily slip your mind. And in this case, it's just, unfortunately, a straight piece of theory that you kind of know or you don't. In this instance, current is actually defined as the flow of charge. And the marks were actually going for that keyword flow, the flow of charge, these two key terms being the flow and actually of the charge. So there was 6 marks going for this total question, and the breakdown was fairly simplistic. 3 marks going for this word flow, and another 3 marks going for the word charge. In part 2, we were asked a more mathematical question. In this case, we're asked to calculate the current flowing when a mole, 6.0 by 10 to the 23 of an electrons passes a point in 30 minutes. Now, this can seem a little bit more difficult off the top of your head. And, if you don't do chemistry or you're not massively familiar with kind of that side of science, you wouldn't really understand what the mole is or mightn't have even encountered it. But in this case, it's not massively important. It's just a number of electrons, basically. The way we solve this first problem is simply by multiplication. All we have to do is multiply 6.0 by 10 to the 23 electrons by the amount of charge per electron. This figure can be found in your log tables on the charge of the electron in the constant section of your log tables. Very, very useful. Something that comes up all the time, especially in this part of physics. And that number is 1.6 by 10 to the minus 19 coulombs. And simply by multiplying these two out, we will get a value for the total charge that is associated with 6.0 by 10 to the 23 electrons. I'm now going to plug this into our calculator. So we're going to have 6 by 10 to the 23, and we're going to multiply that by the charge on a single electron, which is 1.6 by 10 to the minus 19, and that's going to give us a total charge here of 96,000 coulombs. So massive charge here, and we're just going to write that down. In this case, unfortunately, this formula for current isn't actually included in our log tables. And it's just one of the formulas that you either have to know of, or you can actually find using the definition we gave earlier. The definition we said earlier was that current is defined as the flow of charge. Basically, it means the rate of charge that passes through a point per given time. Basically, if we use that definition, we can say that the current, in this case represented by the letter I, is going to be Q divided by T, or the current flow, Q per unit time. As a result of this, we can plug in the information that we know. On the top, we're going to have our charge, which we said was 96,000 coulombs, and on the bottom, we're going to have our time. Now, time, as always, is going to be in the SI unit, so it's seconds, so we cannot work with this 30 minutes in its current form. So we're going to do 30 times 60, which is the number of seconds in a minute, and we're just going to simply put that into our calculator, and we're going to get a value for the current passing as a result of these 6 by 10 to the 23 electrons over the course of 30 minutes. Now here in my calculator, I'm going to plug in our numbers. So on the top, we're going to have our charge, which we said was 96,000 coulombs. And on our bottom half of the fraction, we're going to have 30 minutes times 60 seconds per minute. And we're just going to hit equals here, and we're going to get a fraction. So just to convert that to decimal, we're going to have 53.3, and the SI unit for current is amps. So as I said before, we're going to have our answer as 53.3, and we're going to have A as our symbol for current, or amps. In part 3, we are given another block of text that we have to kind of explain in this case, a phenomenon. So in this text, we are told that there is a previous definition for the ampere, which was based on the phenomenon of two parallel current-carrying conductors exerting on a force on each other. And we are asked to explain why this occurs. Unfortunately, this is just another theory definition that you kind of just have to know off. And to be honest, I always thought this is one of the more annoying ones, kind of understanding how this works. But in this case, the explanation goes as follows. Each current-carrying wire generates a magnetic field which interact with each other, and thus both wires will experience a force. It's a rather simple definition, but the mechanics behind it can be a little bit more complicated. Basically, what it means is when a current passes through these wires, what's going to happen is each wire is going to build up and generate a magnetic field. As a result, these magnetic fields are going to interact with each other, and when they interact with each other, they exert a force upon each other. And that's just the most basic definition of the ampere in this case. As with all of these kind of more definition-based questions, or explanations, there are a few key points you have to include. In this case, the first key point is saying that each current-carrying wire has a magnetic field. The word interact here is quite important because it basically is showing that the force is felt as a result of both of the fields actually interacting with each other. The breakdown for the marks for this question go as follows. There was 7 marks going in total, and there was 4 marks for saying that it was a result of these magnetic fields that were created by the current carrying wires, and the fact that they were actually interacting with each other is what caused this force to be felt by both the wires. In part 4, we are asked to describe a laboratory experiment to demonstrate this phenomenon. This phenomenon, obviously, kind of going back to the last question, which was the wires feeling a force on each other. Yet again, this is just another kind of definition that you have to know off, or in this case, it's just kind of like a demonstration, which you kind of just have to know off. And I mean, when I was studying for physics, I unfortunately overlooked these until way too late, so caused a lot of panic for me, but I highly recommend you kind of understand them because they enhance your understanding of the material. So in this case, and the experiment that is, you're required to know is that what you need in order for it to work is a power supply and a U-shaped piece of foil. When power is actually supplied to the apparatus, the foil moves as it interacts with these generated magnetic fields, and that's just kind of the most simplest kind of bare bones demonstration that you do in this part of the electronics or electricity section of the physics. The key terms that you need to include here were the U-shaped foil, as well as this having this power supply. Another important thing to note here was that you were allowing this current to flow, and finally saying that the foil actually moves as a result of this current flowing. The breakdown for marks in this question was a total of 9 were going, and they were broken down as follows. 3 marks for each of the key points. So the first important thing was mentioning the pieces of equipment in the apparatus. So 3 marks going for saying that there was a power supply and a U-shaped foil. Another 3 marks were for saying that the current was actually allowed to flow, so this section up here, saying that once current was passing through it. And finally, the last 3 marks were given for saying that the foil moves and thus proves this kind of phenomenon, because the foil wouldn't move unless a force acts upon it.